right, here we are, section 6.4, energy and enthalpy. At the end of this, you'll be able to summarize the roles of enthalpy and heat flow in our chemical reactions, and you'll be able to calculate pressure volume work. Okay, so pressure volume work is work done when there is a volume change as measured against an external pressure. Work, pressure, P, and the change in volume, delta V, are related through this equation right here. Work is our W is equal to negative P pressure times our change in volume. So our change in volume is going to be the final volume subtracted from the initial volume. And 1 liter times atmosphere, or 1 liter atmosphere, is equal to 101.325 joules. So essentially what this is going to enable us to do is it's going to say, well, we can look at something like this scenario right here where we're seeing this piston forced upward. We would be able to calculate the work that was required to get this piston right here to start in this A position to end in this B position. Now, an example calculation would be something like this. A chemical reaction is performed in a flask that is sealed with a piston. Okay, the initial volume, so I'm going to write V initial, and I'm also going to write out my equation. Delta V is equal to V final minus V initial. The initial volume is 0.550 liters, and the final volume, V final, is equal to 0.375 liters. Okay, so if we were to plug this into our equation right here, delta V is equal to 0.375 minus 0.550, that's going to be negative 0.175 liters. Okay, now we'll probably use that in just a second, but I'm going to go ahead and hold up here. Okay, so calculate the amount of work performed in joules during this reaction. Okay, so my equation for that is going to be as simple as, just a second, as W is equal to negative P, our pressure, times our delta V. Okay, well, because I saw in my equation initial and final pressures, volumes, I wanted to go ahead and get that information. So W is equal to 1, or negative 1.00 times negative 0.175. And that would end up being, well, 0.175 liters atmospheres. Now, this question is asking us in joules. Okay, well, in order to solve that part of the equation, we have to go ahead and complete this conversion and say 0.175 liter atmospheres. Do the dimensional analysis to say 1 liter atmosphere and 101.325 joules. That is all equal to approximately 17.7 joules. Okay, so there's our question A, or part A for this question. Now part B reads, determine whether the piston moves upward or downward over the course of this reaction. Okay, now the sign of this equation, or the sign of our answer, is positive. So the surroundings do work on that system. Now that is supported by our negative delta V. So think about it like this. We have, and I'm just going to draw kind of a simple container. There we go. And here is our piston right here. Our initial volume was 0.550. Our final volume, so V sub I, our V sub F, our final volume, was 0.375. So what that means is that this went down, or our piston level, this is my piston that I'm drawing right there, our piston level went down. So the space that our reactants were in got smaller, in which case that means that the pressure or the work was forcing this piston downward. Okay, so that means that our long story short, our piston moves downward. All right, now we're going to change gears just a little bit. We're going to be talking about enthalpy. Enthalpy, well, most chemical reactions are performed in open systems with exchange of both heat and work between the system and the surroundings. Chemists are more often interested in the flow of heat in systems at constant pressure. So we saw that last question where our pressure was 1 atmosphere throughout the entirety of the reaction, that piston moving up and down while our pressure remained the exact same. Now, enthalpy is a state function that relates to the internal energy, pressure, and volume. And it's defined as H. So anytime you see H, I want you to be thinking about enthalpy. That is equal to the internal energy, the pressure, and the volume. Now, enthalpy and heat flow. At constant pressure, the change in enthalpy, delta H, that's what we're generally going to be talking about when we talk about enthalpy. The delta H can be described in the following different ways. Delta H is equal to delta U, a change in internal energy, plus P times the change in volume. Okay, now delta U, a change in your internal energy, is equal to the heat plus the work. Okay, so then you could kind of sub in this Q plus W for delta U. So that's what we're seeing there. Now W is equal to negative P delta V. And so we sub this out right here for, well, this negative W. Therefore, when you do all this simple substitutions, or when you have these different definitions and you do these substitutions, we end up with delta H is equal to the flow of heat at constant pressure, or delta H is equal to Q sub P. So what we can do with that is we can look at constant pressure, delta H greater than 0 when heat is transferred from the surroundings to the system. So from is our key word there, from surroundings to the system. Reactions that absorb heat from the surroundings are known as endothermic reactions. So this is heat kind of coming from the exterior to the system. This is an endothermic process. It's taking heat from outside of itself. Now delta H is less than 0 when heat is transferred from the system to the surroundings. So reactions that transfer heat to the surroundings are known as exothermic systems. I always think of it as a exothermic reaction exudes or releases heat. The heat exits that system and goes to the surroundings. Now, here's an example. Wood is burned in an open fireplace. The reaction releases 250 kilojoules of heat and does 15.0 kilojoules of work on the surroundings. We've got to answer a couple of questions. Determine whether the reaction is endothermic or exothermic. Okay. Then calculate delta H for this reaction. Then calculate delta U for this reaction. Okay, so what we have here is a couple of things going on. The first thing is that we've got heat coming from our reaction. And so heat is going to be transferred from the system to the surroundings. So our delta H is less than 0. In fact, it's 250 kilojoules. Well, this is an I'm going to go ahead and circle it rather than write it. This is an exothermic reaction. It's releasing heat to the surroundings. Okay, so that's question A. Now B Okay, our change in enthalpy, our delta H for this reaction. Well, we've got an open system here. So our delta H is equal to Q, which is equal to negative 250 kilojoules. And what I did there, this is kind of subtle, but I took the information, or I took the description here and basically translated this description. Heat is, or the reaction releases heat, and I used that to give me this negative value here. So an exothermic reaction, your delta H is going to be less than 0. It's an exothermic reaction. Heat is being lost from that system. That is going to mean whatever this says. So the reaction releases 250 kilojoules. Well, whenever you're defining that in terms of a delta H value, that's going to be a negative number. So one thing that you maybe want to watch out for is if this said the reaction absorbs, that word right there should say, oh, well, it's absorbing heat, so it's bringing heat from the surroundings into itself. Therefore, it's an endothermic reaction. Therefore, my delta H is going to be a positive value. I hope that was helpful. Okay, so that gives us that value. Now, the last one is our delta U. How would we calculate this? Well, delta U is equal to Q plus W. Okay, now this Q we actually just defined right here. That's negative 250 kilojoules. Now work done, and does 15 kilojoules of work on the surroundings. So that's work done to the surroundings, in which case this value is also going to be a negative value. So it's negative 250 plus negative 15 kilojoules. Therefore, our delta U, which is a state function, a change in internal energy, delta U is equal to negative 265 kilojoules. Okay. Now, I hope that was a helpful explanation. We're going to do one more practice problem next. Never mind, we're not going to do one more practice problem. Really what I wanted to do is use this as an opportunity to bring back our equations and to look at those and think about what those are. Work is equal to negative P times delta V. So negative pressure times a change in volume. Okay. Next up is delta H is equal to delta U plus P delta V. So that's relating our heat of a reaction to the internal energy to ultimately work done by a system. So a change in heat of a reaction is equal to internal energy plus work. Now, the change in enthalpy of a system, delta H, is equal to the flow of heat at constant pressure. So delta H is equal to Q sub P. Okay. Now some of this might be a little bit tricky, but I know that you guys got that last question, that last practice problem that we did. So there will be some more practice problems that we do in lecture. So make sure that you stay on top of those, but you've got this, so you're good to go. All right. Well, we will continue on in the next video. Thank you very much. Have a good one.